So, let us start lecture 23, and the course is on phase diagrams in single component and binary systems. Today's topic will be based on a multi-component system, and while treating multi-component system, we will take reference with binary system, binary gases rather, and we will try to see when binary gases are mixed in a system, how the mixing enthalpy, mixing entropy, and finally, free energy of mixing would relate. In fact, with the knowledge what we will have while treating ideal gas mixing, we can take those knowledge to the system where condensed components will be mixed. So, the today's topic is multi-component system and mixing of ideal gases. That will be our treatment. In fact, why we need this? Since we have studied phase diagram in single component system, and there we have seen how to arrive at a situation when two phases or three phases will be under equilibrium with the condition that free energy will minimize. That was the condition, and on that basis we could draw phase diagrams in case of water, phase diagram in case of CO2, as well as phase diagram in case of iron. Okay. So, now gradually we will switch to multi-component system, and initially we will treat with respect to multi-component system, that means more than 2 or 3 or 4 components in a system, and then finally we will switch to binary systems where 2 components will exist in a system. There could be multiple phases, but components will be 2. So, let us get to the ideal gas treatment. See, in order to understand the mixing of ideal gases, we need to understand couple of things. The first thing what we understand is the standard state. Okay. So, what do we mean by standard state? In fact, in thermodynamics we always loosely say that standard state is basically nothing but the value of some thermodynamic parameter at 298 Kelvin and 1 atmosphere pressure, which is not typically right. Rather, we will see how to rightly represent standard state. So, while doing that, let us start with a single and ideal gas. Okay. Let us start with an ideal gas. So, it is a closed system, and it is a fixed composition. So, we have these two conditions. If we try to see the governing equation with reference to Gibbs free energy, that equation looks like this. Fine. Now, if I try to keep T constant again, that means one more condition we are applying, then we can get free energy change with reference to change in pressure. Okay. So, now and this is basically G is the molar free energy, since we are starting with 1 mole of an ideal gas. So, from here I can get delta G, G1 when pressure equal to P1 with a temperature T, and G2 pressure equal to P2 at temperature T should be equal to V dP. Since temperature is constant, this term goes to 0, and since we consider 1 mole ideal gas, the equation of state would be PV equal to RT. Hence, I can write volume in terms of P. So, this becomes this. So, I can apply this to this. So, then I can write equal to dP RT by P, where it is P1 to P2. So, this becomes G2. So, this is the final value at P equal to P2 at T minus G1 P equal to P1 at T equal to RT ln P2 by P1. That should be the equation after integration. Here comes the consideration of a reference value. Reference value, and these reference value will give us an idea of standard state. Okay. The whole treatment, whatever treatment we are doing, just to understand standard state. G is a state function and of course extensive quantity, and interestingly absolute value of G is not available. G cannot be decided. Okay. So, that is the issue with G, but definitely we can actually calculate delta G, which is the difference in Gibbs free energy with respect to function of P t or n, let us say n I. I put a condition that let us say if it is not one ideal gas, rather a mixture of ideal gas, then I have to introduce the composition factor, which is included in this function as Ni, the number of moles of different component ideal gases present in the system. Okay. But since in this case it is a temperature constant, composition constant, so this would be a function of P only. We have considered T constant, fixed composition, closed system. So, that has to be function of P. So, change in P we can calculate the free energy difference. Now, so then this equation can turn a bit into G2 P equal to P2 T equal to G1 P equal to P1 T at T plus RT ln P2 by P1. We need to find out this value. If we do not get this value, we cannot find out, at least we can find out this from this equation, but we cannot find out. So, let us say I need to find out the what will be the final state. So, then I need to assign some value to this, assigning some value. Okay. Or we can say a reference value or reference state, okay, from which the changes are to be calculated. So, this reference state is called standard state, and it is basically when pressure equal to 1 atmosphere and temperature, whatever temperature we try to consider. So, it can be 0 degree Celsius, it can be 298 degree Kelvin, 298 Kelvin, that means 25 degree Celsius, it can be 100 degree Celsius, it can be 1000 degree Celsius. The temperature could be anything, but the pressure should be 1 atmosphere. So, why this pressure to be 1 atmosphere becomes very convenient? If you see that these two quantities, so these two quantities I can write in this fashion, RT ln P2 minus RT ln P1. Okay. So, hence I can see that G1 P equal to P1 equal to 1 atmosphere at T equal to T is having a relation with RT ln P1. Now, if P1 becomes 1 atmosphere, then in that case I can take it P equal to 1 atmosphere, T equal to T equal to, or I can say G naught at T. Okay. So, that we consider as standard value, fine. And if I take 1 atmosphere, so this is not equal, this is assigned a kind of standard value. So, this becomes 0. So, remember this is not equal to 0, rather this is taken as a standard value, okay, at T when the pressure becomes 1 atmosphere for that particular ideal gas. And remember here we have considered only one single ideal gas. So, then one more consideration is coming into picture, pure gas. So, that means no other mixture. So, that means this is considered to be for the pure gas. So, then final equation turns out to be G P equal to P to become P, that the final pressure at T should be equal to G P equal to 1 atmosphere at T with a naught. So, the standard state is given as a small 0 as a superscript, and that becomes standard value, standard state, plus RT ln P. Okay. So, why we are taking P equal P1 to be 1 atmosphere? We could have taken P to be P1 to be 2 atmosphere, we could have taken P1 to be 3 atmosphere. So, it is basically a reference value. Accordingly, we can measure this RT ln P2 by P1, fine. So, but if I take P1 to be 1 atmosphere, then I do not have to consider the initial pressure, because I know that is 1 atmosphere. So, the ln 1 becomes 0. So, whatever pressure I need to consider is the final pressure, okay. And the standard state what we have taken as G naught at temperature T, that is to be added up with the RT ln P. Okay. So, this becomes my final expression. So, now we see it can be, instead of writing P2 all those complications, I can simply write G T equal to G naught T plus RT ln P. I can write this, where G naught T is the standard state at temperature equal to T, and here remember this becomes for pure gas. Okay. It is not for mixture, it is a pure gas system, fine. So, that becomes, that is the philosophy of standard state, and remember this is a reference state. Let me just give you an analogy. For example, let us say if I want to calculate height of a kind of person, then I take the sea level as a 0 height, okay, and accordingly I can calculate the person's height, fine. So, that becomes let us say a 5 feet. Now, if I take Everest top to be my reference value and the person is standing on top of the Everest, then I can still find out what is the value of the person's height. Still it would become 5 feet, because finally the height is nothing but the difference between the top level of that particular person, head top value or the height of head top with reference to the Everest top. So, it still becomes 5 feet. So, the difference does not change. Okay. Here also the standard state value, the difference does not change even if I take P1 to be 1 atmosphere or 2 atmosphere or 3 atmosphere, but 1 atmosphere makes my life easy, because that long term does not have to consider some complicated values, ln values. Okay. So, that way P1 equal to 1 atmosphere becomes the most convenient value. Another thing is, whenever we talk about 1 atmosphere, that means is basically the pressure exerted on air pressure which is existing in the atmosphere. Okay. That is also 1 atmosphere. So, that means any natural process occurring would be occurring at a 1 atmosphere pressure if we consider that is occurring under normal atmospheric pressure. So, which is 1 atmosphere. So, again that 1 atmosphere has a consideration of 1 atmosphere makes sense. Okay. So, that is what that standard state value is referring to, 1 atmosphere, and temperature could be anything. Now, we say that standard state is basically 1 atmosphere 298 Kelvin. Instead of that, we must say that standard state value at any other temperature, let us say 1000 Kelvin, okay, or 500 Kelvin, any value, but whenever we put this, it makes a sense that this is for pure substance as well as when pressure equal to 1 atmosphere. Temperature could be anything. Temperature could be anything, and it is basically the temperature where we are trying to measure the value, the difference in value of that particular free energy. Okay. So, if you see here also, we have considered the T to be constant. If you see the initial beginning of the treatment, we have given the T to be constant. So, that means at that constant temperature, the effect of pressure we are calculating, and we are trying to measure the difference in the state variable. Okay. So, now at least we should be clear that it is not about 1 atmosphere and 298 Kelvin, it is about 1 atmosphere pure substance and temperature of consideration, it can be any temperature, fine. So, and that time we reflect it with a superscript 0, okay. So, we call it not. Now, while discussing this, we do not know what is the value, okay. It could be anything. Now, while doing that assignment, we also assign some values, okay. Let us see in electrochemistry. Electrochemistry, we assign free energy of hydrogen plus ion to be 0 at 298 Kelvin and 1 atmosphere pressure. So, since it is not, it is 1 atmosphere, and here we could calculate let us say 0 joule, fine. Okay. At the same time, this is our assumption H2 gas is also 0 joule at 298 Kelvin and 1 atmosphere. Okay. So, these are all reference value, and these value are zero is assigned. Actual value could be something, but we are assigning 0. And why we assign 0? Because when we talk about standard hydrogen electrode and that potential is E naught is nothing but 0, and how come it comes? They make use of these two values. and it can be termed as chemical potential of hydrogen naught or chemical potential of hydrogen gas naught. Okay. And when it is pure, since it has to be pure, so when it is pure, that means the molar free energy and partial molar free energy, those or chemical potential, they are equal. We have seen before, okay, in case of pure substance. So, I can write mu naught H plus or mu naught H 2, they are to be the molar free energy of H plus or H 2 at 1 atmosphere, and here we are specifying 298 Kelvin. So, any other temperature this value is not 0, rather some other value. So, now that is what the standard hydrogen electrode we have 0, and how we calculate that? We calculate from this equation, and here N is 2. Why? Because we are taking this reduction process, and that time if we try to find out delta G naught, which is nothing but G H 2 naught minus H plus 2, since both are 0, so it becomes 0, and that makes a sense that E naught becomes 0, okay, 0 volt, 0 volt. So, we know that the standard hydrogen electrode potential is 0 volt. Why it is 0 volt? Because we have already assigned some values for the H plus as well as H 2 at standard state. What is the molar free energy of those when the temperature is 298 Kelvin, and remember here it is applicable 298 Kelvin at 1 atmosphere. Fine. So, this is one. Now, in case of electrochemistry, whenever we try to see a stable phase at 298 Kelvin, okay, for example, hydrogen gas, if I consider 298 Kelvin, 1 atmosphere pressure, the stable form of that gas is gaseous phase, okay, it is not liquid or it is not solid. Okay. So, that is what the stable component, and that too pure, and if I take 1 atmosphere and 298 Kelvin, then that value is nothing but 0, that is assigned value. For example, similar way I can assign, so this is assigned nickel when it is solid at, because we know that whenever we are putting naught, that suggests that it is 1 atmosphere. So, this is, and but temperature we have to mention 298 Kelvin and 27 degrees Celsius, nickel, the stable form, most stable form is solid. Okay. So, that value is taken as 0, but here chemical potential of nickel plus plus at 298 Kelvin is not 0. So, the only one case when it is H plus at 298 Kelvin 1 atmosphere, that is assigned as 0 joule. Why? Because in order to get that standard electrode, standard hydrogen electrode, that electrode potential to be 0 volt through this calculation. Okay. Similarly, I can find out naught O2 at 298 Kelvin, is still 0 joule. Okay. So, this gas is the most stable phase of oxygen at 298 Kelvin. So, these are basically assigning some value, and the 0 is the best possible value, because whatever value we will calculate with reference to 0, that would be simply that value only, with the difference is basically either positive or negative. If the potential goes negative side, then this mu value would become positive. If the potential goes positive side, the mu value would be negative. Okay. So, that is the only difference, that positive or minus, but since it is assigned 0, calculation becomes easy. Now, on the other hand, another thing, so this is with reference to electrochemistry. Now, if I talk about enthalpy, and when we talk about standard enthalpy, let us say this is become standard since it is 1 atmosphere. Let us say that time also 298 Kelvin if I consider for aluminium, and that case this would be 0 provided aluminium is solid, because 298 Kelvin is at that temperature aluminum, the most stable form of aluminum is solid. So, then again that is actually given as 0, and remember these are for all mole. So, I can say mole 1 mole substance. Okay. So, these are all mole, you just put mole value. So, joule per mole, because we are trying to calculate per mole. Okay. So, if it is solid, aluminum is solid. So, that case enthalpy, standard enthalpy at 298 Kelvin for aluminum, when aluminum is solid, that is 0. But if I consider 298 Kelvin for liquid aluminum, that time it is non-zero, rather it is greater than solid aluminum. Okay. In fact, I can also say like this. So, with reference to this, those values will vary, because we know the enthalpy of high temperature phase, which are basically liquid or gas, will be more than the low temperature phase, like that variations would be existing. Similarly, if I consider standard enthalpy 298 Kelvin for oxygen, this is 0 when oxygen is gas, because at 298 Kelvin 1 atmosphere pressure, the most stable form of oxygen is gas. So, that time I can assign a value to this oxygen enthalpy at 298 Kelvin is 0. So, now these are all absolute values. We do not know what is the actual value of that, but we are just assigning, and it does not make any problem in our final calculations, because the final calculation would always try to see this, okay, the difference in enthalpy rather than absolute enthalpy. Okay. So, then it will be absolutely fine, and if it is considered as 0, then so it is nothing but this goes to 0. So, I do not have any problem in calculating delta H naught at 1 atmosphere, above as we increase the temperature from 298 to let us say 1000 degrees Celsius, I still would be able to calculate, because that calculation becomes very easy, since I have considered the standard reference to be 0. Okay. So, that is the beauty of assigning some value to some of the standard functions or standard variables. Okay. So, that way we handle the calculation, thermodynamic calculation, and we also find out what is the final difference of those variables, state variables. Okay. So, let me stop here. We will take this particular fundamental idea of standard state when we try to see the mixing of ideal gases. So, till then let me stop now. Thank you.